And we're looking at the way that matter is structured using the idea of charges is our way of looking at it. Now, before we really talk anything about like the structure of matter, because I guess that's really more the domain of chemistry usually, right? And so we're maybe thinking about subatomic particles a lot here. We got electrons and protons. And of course, electrons are negative and protons are positive. But I want to talk about how the force works. So there's this thing called Coulomb's law for the magnitude of the electrostatic force. And electrostatic force is that force between two or more charges. Two or more point charges is how we're going to talk about it. And there is an electrostatic constant. Now I'm going to lead off with the idea of an electrostatic constant because this electrostatic constant, which I'm going to write as 9.00 times 10 to the power of 9 Newton meters squared per Coulomb squared. And if you see it written as anything else on an equation sheet or something like that, you roll with that equation sheet. Okay, if you see it written as something slightly different in a textbook with different number of significant figures, you roll with that. Okay, but for now, we're going to go with this 9 times 10 to the power of 9. Easy to work with. But that constant fits into a formula that actually looks very familiar. So I'm going to write it as force subscript E for electrostatic force, the force between two charges, and it takes on the form K Q1 Q2, and I'll pause there for a second. The K that I've got here is this constant, this electrostatic constant. And maybe I should even say that electrostatic constant that I just stated is specifically for in a vacuum. Because it would be a little bit different if it was underwater or in wood or something like that, okay? And that has to do with the properties of the space that you're in. But electrostatic force is K times Q1 times Q2. And again, I'll pause and point right here. I've got a Q1 and a Q2. Q1 is charge 1, Q2 is charge 2. I don't know, in chemistry, capital Q is for quantity of heat energy. In this context, Q is for quantity of electric charge, quanta of electric charge. It's actually quantized, whereas the heat energy isn't quantized. And then divided by r squared. And as soon as I write that 1 over r squared, what formula does this immediately make us think of? Yeah, immediately. Universal law of gravitation. And it turns out that Coulomb was developing his law around the same time that Cavendish was developing his law. And so like there are these, ideas that are possibly traveling between circles. And we can go into the history of that if we wanted to, but I don't want to go down that pathway right now. Let's just label this up quickly. These Q values are the charges. And the charges are measured in units of, well, it's Coulomb's law. So charge is measured in units of coulombs. Capital C. It's the last person's last name, so we capitalize. And the distance between those two charges is the R value, just like in gravity. Now, when I look at these two charges, maybe you can see, maybe you can't, there's a plus sign inside of the charge on the right. There's a minus sign inside of the charge on the left. We've heard this before. It's something that people throw around out there when they're talking about dating advice or something. Opposites attract, right? Now, that's probably not entirely true, and probably people that are like-minded would get along better or something. But opposites attract is what people often say. And then likes repel. Yeah. So I've got positive attracting negative. I got negative repelling negative. I've got positive repelling positive. Okay. And so when I look at the notation here, notice as well, the way I've even written it is force of 1 on 2, force of 1 on 2, force of 1 on 2. This really is a Newton's third law force. These are mutually acting on one another. So if there's a force of 1 on 2, there must be a force of 2 on 1. It really is Newton's third law. It's just that there's no rope or tension or anything like that. It's a field interaction, right? So it's a field force. And we've talked about this with force due to gravity, universal law of gravitation. It's also a Newton's third law example, but with a fundamental force rather than like a contact force or something like that. All right, so we've got these ideas of attraction and repulsion and the fact that it's a action-reaction force. One other thing I want to throw out here, which isn't really a part of the concept, it's more of a unit thing. because it's so important in terms of the units. It comes up so often. Oftentimes you'll see things measured in microcoulombs. Now, the reason that you measure them in microcoulombs is because a coulomb of charge is like a small lightning bolt. Like, I mean, a coulomb is big, actually. A microcoulomb is typically what we deal with. And why the coulombs themselves weren't scaled down to be on the scale of microcoulombs, I don't really know. I'd have to do some reading on that one. But for now, we're just going to talk about the idea of a microcoulomb and recognize that the definition of one microcoulomb is 1 times 10 to the power of negative 6 coulombs, micro being the prefix for millionth. So 1/1,000,000th of a coulomb. And so the reason that's important right away is because right away I want it to be kind of, realistic. So I've got the force between two charges, one of which is 2 microcoulombs and the other of which is negative 3 microcoulombs, and they're separated by half a meter, 0.50 meters. So I want to take stock of what we know. Q1 is equal to 2.0 microcoulombs, and we'll immediately convert that over to coulombs, because we always use our base units, times 10 to the power of negative 6 coulombs. So we got to convert to coulombs before we can do our calculations. That electrostatic force calculation is measured in units of coulombs. We can see that because K has coulombs built into it, not microcoulombs. So we got to convert to coulombs. I'm just trying to figure out how many times I can say coulombs in one paragraph. But negative 3.0 microcoulombs, and the negative sign is a part of the charge. Remember, if it's a negative, it has an excess of what? An excess of electrons or an excess of protons? Yeah, if it's negative, it's got excess electrons. If it's positive, you could either talk about it as an excess of protons, or a lot of people will talk about it as a deficit of electrons. The reason it would be thought of as a deficit of electrons is because electrons are the mobile charge, right? So we talked about ionization or things losing charge, electronegativity they talk about in chemistry class, but somehow electrons have been stolen from something to make it be positive. We don't deposit protons. That's just not the way charge gets transferred. So negative 3.0 times 10 to the power of negative 6 coulombs. And sometimes people say, well, why don't you transfer protons? Well, because to transfer protons, you'd be splitting up the nuclei. You'd be, I don't want to say committing nuclear fission because that makes it sound like a crime, but you'd be splitting up the nucleus and then sending protons to another cluster of atoms. That's not how charge gets transferred, because nuclear fission should never just be like a casual process, right? Whereas if I rub my shirt up against a balloon, I definitely lose electrons or gain electrons. I'm not losing or gaining protons. By golly, if I could do nuclear fission by rubbing balloons on my sweater, the world would be a wild place. So the R value is 0.50 meters. And then, I mean, this is just plug and play kind of problem. This isn't even rearranging. I wouldn't even call this problem solving. This is just making sure we can do the data entry on this. So force of 1 acting on 2 would be KQ1, Q2 over R squared. Don't forget that K value, 9.00 times 10 to the 9, Newton meters squared per Coulomb squared. So it's not any less ugly than the universal gravitation constant. And here I haven't left myself very much space, so hold on. Let me see if I can surf my way underneath the here. 2.0 times 10 to the power of negative 6 coulombs times negative 3.0 times 10 to the power of negative 6 coulombs divided by 0.5 meters. Don't forget to square it. Now, can you guys see if you can plug that in? See if you can put that into your calculator, because there's a bunch of scientific notation there, and that's generally the thing that we mess up on these things. I'm going to say that there's a 6, a 1, and a 2 in this, but not necessarily in that order. Anybody agree? Yep. 0.216, yeah. 0.216 newtons, positive or negative? Negative. Now, I can round this off to, looks like only 2 significant figures. 0.22 newtons. The thing is, what does it mean to have a negative force? Because both of these charges would experience a negative force, so it can't. Oh, sorry, I guess we're talking about these two charges. So the fact that it's negative can't really be a reference frame thing. In code, a negative force means attraction. It's not a reference frame thing. So what people will frequently do is they'll just absolute value these guys, and they'll say toward each other. Now, in the next question, the very next question, we do need to use a reference frame. But I want to draw attention right now that this negative sign isn't a reference frame negative sign. It really is just code for attraction is happening here, okay? Because opposites attract, which is really why I also wanted to list out these pictures, was to show, yes, opposites attract, so negative sign must mean opposites attract, because if I did the exact same process and both of the charges were negative, wouldn't that have been a positive answer? Negative times a negative is positive. That means repulsion. Positive times a positive for the two Q values, again, positive, therefore repulsion, right? So we're maybe linking up this idea of what positive and negative means and hanging our hat on this concept of some silly thing that we heard about dating once before, about opposites attracting and like things repelling or something like that. All right, so I want to pause there, and we'll look at